Today we are moving on talking about continuity, strongly related to limits. So continuity, like if we were to, what does it mean? I kind of got this out of order just a little bit, I think. What if we were to, let's go here for a second. An informal definition of continuity is this: a function is continuous where I can graph it without taking my pen off the board. So any place during the period of graphing the function at any value of x where I would have to take my pen off the board, the function becomes discontinuous there, right? That's a discontinuity. Okay, so if we were to discuss like the continuity of this function here that we've seen several times, let's briefly look at it again. It's worth seeing again. What would we get? Okay, so we've kind of talked about how we split an absolute value function up into pieces, make it a piecewise function. What about the absolute value of x minus 2? Well, the absolute value of x minus 2 is going to equal x minus 2 whenever it's positive valued, whenever x minus 2 is positive valued, right? Well, when is x minus 2 positive valued? We could just solve the inequality and find out. X minus 2 is greater than 0 whenever x is greater than 2, right? So that's how we get this domain. It's equal to the opposite of x minus 2 whenever x minus 2 is negative valued, which is when x is less than 2. So then we could build the function absolute value of x minus 2 divided by x minus 2 by just dividing each piece of this piecewise function by x minus 2, right? Like we did previously. So we would just end up with the piecewise function x minus 2 over x minus 2, which is 1, whenever x is greater than 2. The opposite of x minus 2 over x minus 2, which is negative 1, whenever x is less than 2. And the function would be undefined at x equals 2 because that's a place where we would have a 0 on the bottom, right, which we can't do. So if we were to graph this thing, that's what we get. We'll discuss the continuity of this function. Not much to say except at one place. What's that? Okay, what happens at 2? It jumps, right? So we'd say the function is continuous everywhere except at 2. There's a discontinuity at 2, okay? Okay, so then let's start off when we want to define continuity, and our goal is we want to build up a definition of continuity on intervals, which sounds complicated, but it's not really. It all depends on how we define continuity at a point, because any interval is just a collection of individual points. It's an infinite number of individual points, but it's just a collection of individual points. What we're going to end up saying is that a function is continuous on an interval if it's continuous at every point on that interval, right? So we need to be able to understand, how do we define continuity at a point? Well, there are 3 conditions, 3 criteria we have to satisfy for a function to be continuous at point A, where x equals A. The first one, that's not the first one, that's the first one, is this: the function is defined at A. F of A is defined, okay? Now let's think about this in terms of our trusty ant. What does that mean to an ant if an ant's walking on the function? If the function is defined at A. Say it again. Yeah, he can step there. He has a place to stand, right? Okay. Right, he can step at x equals A. There's firm ground for him or her. What about this one? The limit of the function as x approaches A exists. What does that mean to an ant? Oh, here, I guess I didn't. Right, the ant has a place to step. Okay, I forgot I had those written out. So what does that mean to an ant if the limit of the function as x approaches A exists? Say that louder, Rachel. Okay, he's not going to step on A, right? The limit doesn't mean he's stepping on A, but what can you tell me about as he approaches A? What that tells me something important. Slightly more than that. I'll give you, say it again. He's getting really close to it. I'll give you a little hint. Finish the sentence. Ants approaching A from either direction will what? If the limit exists, what's it for a two-sided limit to exist? What has to happen? Right? What's our fundamental definition of a two-sided limit? What has to happen if the limit as x approaches A exists, then ants approaching from the left and from the right better agree on something, right? What is that? Say it again. You're getting there. What has to be equal? The limits. Okay, right. The limits from the left and the limits from the right have to exist and agree, right? Does that make sense? Remember that definition we added a little bit ago? A regular two-sided limit only exists if the two one-sided limits converge on the same value, right? Okay, so that means that ants approaching, well, what's this mean then? That means ants approaching from either direction anticipate stepping on the same place. Okay, now they're not in the limit, they don't get there. They just anticipate stepping on the same place. Okay, and that's real. I'm going to underline that because that anticipate is important. What do you think the final criterion is going to be? The function has to exist at A. The limit has to exist at A. What's the last piece of this puzzle that probably has to happen? What probably has to be true about the places that the ants anticipate stepping if the function's going to be continuous? It what? It's got to be there. Okay, true. But what do you mean by that? Okay, the place they anticipate stepping has to be. Okay, sure. Okay, but what about a function like this? No, you're right there. You're just about. Oops, what'd I do? I gotta be there. Where'd I go? Did I just delete it?
You'll just get close. I have a black ant. Oh my gosh, this is so cute.
There we go. Continuity.
Yeah, I was with Rachel actually. Yeah. We skipped one day. Where were you? The people helping people. Oh, what? Which one do you?
Okay, does that function fulfill the first two criteria?
Yeah.
It does, doesn't it? The ant has a place to stand when x equals A. Where is it? Right there, right? The limit exists. Ants from either direction both anticipate stepping on the same place, but something went wrong here because that function is not continuous. I had to pick my pen off the board to draw that point, didn't I? Right? So then what do you think? What's got to be the third criterion? Okay, well, but that's the point. We want it to be continuous. We want it to be continuous, but what has to be true about this?
I don't know what you mean. I don't. It has to be on the thing.
Okay.
It has to be on the thing.
How about this one? The value of the limit has to equal the value of the function. Right? Okay. Makes sense because look, in this case, where did I draw that thing? Was it down here at the bottom? Yeah. Look, in this case, the limit doesn't agree with the value of the function, right? See what I'm saying? Okay.
Okay, well that's what I mean.
Okay, and what does that mean to the ant? How would we describe that? What's that mean to the ant if the limit agrees with the value of the function? Perfect. It means he's going to step where he anticipates stepping. Okay? If all those things are true, then the function is guaranteed to be continuous at A. Okay. It's discontinuous at A if any of those criteria are not met. Okay, so let's practice here figuring out what went wrong. So is this function continuous? No. Where is it discontinuous? At 1. Okay, good. So the function is discontinuous at 1. Okay, well, why is that? Because there's a hole there, but which, if we go down and look at all these criteria, let's just check off the ones. We'll put a green check by the ones that it passes, and we'll put a red X by the ones that it fails. Criterion 1. No, it fails, doesn't it? So there it is. There's the reason, right? Whoops, that's not red. Oh, darn it. That's red. Okay, does it pass criterion 2? Yeah, it does. Okay, now obviously criterion 3, if it fails 1 or 2, it fails 3, because 3 wouldn't make any sense, right? Okay, so it obviously fails 3. We could say that the reason it fails, though, the earliest reason it fails is the first criterion, because the function's undefined, right? Make sense? Okay. Okay, how about this function? Okay, so this is a greatest integer function, right? That's all this is. Greatest integer function. If we look at the graph of a greatest integer function, same thing, by the way, as a floor function, right? That's that stair step. We saw this. We've already seen this one, right? So it's an infinite stair step. It's discontinuous where? Everywhere. Well, not everywhere. Okay, but what do we call those? There are certain number values. Okay, well, I'm looking for the right answer. I'm looking for I'm kidding. Mostly. It's discontinuous. How could we describe, rather than, there's got a couple options here. We could say, you guys could take the rest of your lives and not finish this question by saying it's discontinuous at 0, 1, 2, 3, and count forever. And then you got to go backwards too. Or you could say the set of all what? No, real numbers that's a real number. It's fine there. Well, no. What do you call that set of all the hash marks on a number line? All the numbers that, when written as fractions, have a 1 on the bottom. Whole numbers. No, whole numbers start at 0 and only go positive. No, natural numbers start at 1 and increase by 1. Integers, that's it. Integers, that's it. Right, it's the set of all integers. There you go. Okay, and the set of integers are represented typically by Z. That's our symbol for the set of integers. So what are we saying here? X cannot equal n, where n is any element of the set of integers. Okay, that's how you could even probably just say X is not an element of the set of integers. Those are the places where it's discontinuous. Those all say the same thing. Okay, so let's talk here. Why is this true? Okay, well, let's go through our checklist. Criterion 1, check or X? Check, yeah. The function is defined at every integer. The ant always has a place to stand, right? So that one's good. That's a check. The limit exists at each integer. The limit, okay, remember what a limit is? The value that the ant anticipates stepping on. Okay, how come, Grace? You're right. Okay, well, okay, they're open circles. Oh, perfect. Okay, because the one-sided limits don't agree, right? The limit from the left, if the ant is walking towards 2 from the left, the ant anticipates stepping there. But if the ant is walking towards 2 from the right, he anticipates stepping there. Different places. So the limit fails to exist, right? So we get a check or an X there, which means we get an X there. So what's the earliest indicator? What's the most basic? We want to kind of, as we walk down that list of criteria, the first one it fails is number 2. The limit fails to exist. right? So that's why this function is discontinuous. There's no limit, right? I don't know why I said 1, but it would be at any integer, right? Okay. I should probably change that to, here, I can do this. Ooh, this will be tricky. Change it to an n, where n is just any integer. Okay. Good? Okay, how about the continuity of this function? We kind of saw one like this. Okay, let's go through the checklist. Where is this one discontinuous?
No, 1.
At 1. Good. Right.
Oh, okay.
Okay.
Well, you knew what I meant.
Yeah. Yeah. Okay, so let's do our checklist again. Let's do our checklist. So does it meet criterion 1?
No.
Doesn't? The ant has no place to stand at 1?
Yeah,
It does, yeah. So it does meet that criterion.
Yeah.
Does the limit exist? You sure?
What? Wait. I'm so confused now.
Okay, so now
Oh, yeah.
okay, explain. How come? You got it. The light, I saw the bulb go on. Everything lit up. So explain. Why does the limit exist? That's it, right? The limit is there. The ants approaching from the left and the right both anticipate stepping on what y value? 1. They anticipate stepping there, right? So the limit exists. The value of the limit is 1, but the value of the function at when x equals 1 is 2. So it actually passes both of the first 2 criteria, but it fails the third because the limit exists and the function exists, but their values do not agree. Okay, yes?
Okay, why would, so this one, the limit exists and the point's not there, but like the last one with the graphs, and like, why was that one like that?
Okay, why did the limit not exist there? Because ants approaching from the left and the right don't agree on the same point, right? And that's our definition of a limit. Here, let's go back and just write that down. Let me go back to, this is probably worth, the limit of f of x as x approaches a equals L if and only if, right? If, that's what that means. If and only if. So this everything else has to be true here. If and only if the limit of f of x as x approaches a from the left equals L, and the limit of f of x as x approaches a from the right equals L. Okay, remember what we said. The two-sided limit exists if and only if each of the one-sided limits exist and agree. Okay, ants from both sides would have to anticipate stepping on the same y value. Okay, good question. That's why the previous one did not work. Okay, so to summarize, there it is. It's discontinuous because the limit as x approaches 1 disagrees with the value of the function at 1. How about that one? F of x equals 1 over x squared. So it's got an asymptote at what x value? 0. Okay, so let's go through the checklist here. Is the function defined at 0? 0 is our value of a in this case, right? Is it defined? No. Function's undefined there, right? The function's not defined at vertical asymptotes. So we get an x, and the reason being, I'd have to divide by 0. So 0 is excluded from our domain. If we wrote the domain down, the domain up here would just be x cannot equal 0, right? Okay, so we get an x. Does the limit exist as x approaches 0? What do you think? Thumbs up or down? Yes. How come? Hayden, you're right. Because it's an asymptote, right? There's no place, think in terms, we can think in several ways about this. Think in ant terminology. Where does the ant anticipate stepping on the same point from both sides? No. The ant never anticipates stepping on a point because the mountain just keeps getting steeper and steeper the closer he gets, right? So he can never say, there's the point I'm going to step on. It's always infinitely far away, right? And of course, the limit can't exist if the function doesn't exist there, right? If the function's not, well, I guess that's not true. That's a bad way to say it. That's not true. The limit doesn't exist because of this, I guess, right? You could say that the limit of the function as x approaches 0 is infinity, but that's not a number, right? So the limit doesn't exist. For the limit to exist, it has to equal L, which is a real number. That's not a real number. So 3 strikes, this one's out, right? So what could we say here about this discontinuity? It's discontinuous at x equals 0 because everything. There's no limit and there's no function, right? The limit doesn't exist and the function doesn't exist. Okay? Give me thumbs on this. Is that making sense? See how we're getting all this stuff? Okay. Okay, so now let's try to organize types of discontinuities that we could have here. What about a point discontinuity? What do we mean by a point discontinuity? Well, we've seen those. The examples that we've already seen of point discontinuities would be things like that, because it's only discontinuous at a single point, right? There's just one little value there. Same thing here. There's just one little value that's off. A jump discontinuity, that was like we looked at the absolute value function where there was a step, or we looked at the greatest integer function. Those are examples of jump discontinuities where the ant would literally have to jump to get from one piece of the function to the other as he crosses the discontinuity. And then an infinite discontinuity is just any vertical asymptote, right? We're going to go one step further than this. Point discontinuity gets us kind of in the right direction, but there's better terminology. And here it is. We can decide whether continuities are removable or non-removable. Okay, what does that mean? Well, a removable discontinuity is one where the function can be repaired by moving or defining just one single point. All I've got to do is tweak one point and I fix the entire function, right? A non-removable discontinuity is the other kind, right? Non-removable discontinuities would require moving an infinite number of points to repair the discontinuity. Removable, single point will do the job. Okay, so we could just go back to that previous picture that we looked at. And really, the removable discontinuity, what we called point discontinuities, we're now going to call removable discontinuities because they're easy to remove by redefining a single point. The other ones are fine, jump discontinuity and infinite discontinuity. The two combined, these two are examples of non-removable discontinuities. This is the removable discontinuity. Okay? Make sense? Okay? So there, just for your notes. You've already seen this, but we're just going to change that wording to removable discontinuity. Okay, what about one like this? Now, this time we don't have the benefit of a graph. That's the difference. So how are we going to deal with this? We're going to go through our checklist still, right? Okay, does the function, is it defined at A? Yeah, it is. In fact, what is the value of the function at A? A in this case, what's the value of A? Where could there potentially be a discontinuity in this piecewise function? At 2, right? The function 2x is fine. That's going to be, there's no issues with that. I'm going to be able to graph that line without ever picking my pen off the board. Agreed? What about the parabola x squared plus 1? Again, I'll be able to graph that parabola individually without ever picking my pen off the board. But we might have a problem where those two join up at 2, right? So 2 is the issue. Well, what is the value of the function at 2? What is it? 5, right? Okay, because it goes, the function is defined at 2 in the bottom piece, not the top piece, okay? What about the limit of the function? Well, we don't know yet. What am I going to have to do to figure out if the limit exists? You got to throw something out, 'cause I'm just going to stand here. You got to throw something out. Now, just try to think about this. What do we mean? Like, for a limit to exist, what has to happen? Why would a limit not exist? A limit would, say it again, when they don't agree, right? So what would I've got to, I'm not going to say it. You tell me. What do I do then? What they don't agree. What's not agreeing here? What do we call those things? The two-sided limit only exists if the one-sided limits both agree. So we got to find the one-sided limit from the left and limit from the right. Okay, let's take the limit from the left. The limit of f of x as x approaches 2 from the left. Which piece would I be dealing with then? If I'm approaching, which piece is the ant standing on if he is less than 2? Top one. Okay, so I'm taking the limit of 2x as x approaches 2 from the left, which is what? What value is that? 4. Yeah, just 4, right? We're approaching 2. The fact that that minus is there, why is that important? All that's telling us is that we're using the top piece, right? So we get 4. Okay, how about the limit from the right? As x approaches 2 from the right, then we're on the bottom function, agreed? So we're taking the limit of x squared plus 1 as x approaches 2, and what's that going to equal? 5. Okay, so do those equal each other? No. Okay, so we got a problem, don't we? Those are not equal, so the limit does not exist, right? It fails that step, so it fails the third step, so it's going to be discontinuous. So what do you think this thing is going to look like then? The function was defined, but the limit didn't exist. The fact that the limit didn't exist, what's that telling us about the type of discontinuity we're probably going to see here? You know. Yeah. Guarantee you do, because you told me you were steered us in the right direction immediately. So you definitely, if it failed to do what you suggested it needed to do, right? What would you call that? What kind of that's it. What kind of discontinuity is that? Jump. It's a jump discontinuity. Yeah. Right? It's got to be a jump discontinuity because the limit didn't exist. Ants from the left and the right agreed where they thought they were going to stop. So if we actually look at the picture, that's it. There's a jump. Okay? Make sense? Okay? You might wonder why we're doing all this. We're just trying to build some intuition about continuity here. That's kind of what today's about. Okay, how about this one? We don't have a graph. We got to go through this one piece by piece. Is the function defined at, what's a? 1. Okay, 1 is the only place. X squared by itself is fine, right? Y equals 2 by itself is fine. But potentially they don't match up. Okay, so I guess we should say that. A equals 1. So what is the value f of 1? 2. Okay, does the limit exist? What's the limit of f of x as x approaches 1? Well, if x is approaching 1, which piece of the function are we on? No, the bottom is where x is equal to 1. Have to be the top one, right? Every place where x is not equal to 1 is on the top one. And as we approach 1, we're not at 1, right? So this is like saying the limit of x squared as x approaches 1, which is what? 1. Okay, so then we didn't even need to break this into two-sided limits. There was nothing, right? There was no reason to here. As the ants approached 1 from either direction, they were on the same piece of the function. So we didn't need to split this into two pieces in this case, right? It's a simple limit to take. Again, are we gonna meet the criteria for continuity? The function is defined, it's equal to 2. The limit is defined, it's equal to 1. So what about test 3? Does the value of the limit equal the value of the function at 1? No, it doesn't. Look, 2 and 1 are different. So it fails this one. Okay, so what does this one have to look like then? If both the limit is defined, if the limit's defined, it means it's not a jump discontinuity, right? The function is defined, so the ant has a place to stand. What's the only type of discontinuity this could be if the limit exists? It's got to be removable, doesn't it? Right? It's got to be removable because the answer both anticipates stepping on the same point, but we pull the rug out from under them, and that's not where they end up stepping, right? There's someplace different when they get there. So it's going to be something like that. Okay? How about one like that? Okay, this time clearly the 0 is the a that we're interested in. That's the place where we could have issues. What's the value of the function at 0? Okay, yeah, it's 1, isn't it? Okay. What's the limit of the function? Which piece am I on as x approaches 0? Top piece. Okay, so the limit of f of x as x approaches 0 is the limit of the top piece, which is sine x over x as x approaches 0. Now, that's one of our special limits. What's that limit equal to? 1. So we made it, right? This one meets all criteria. Yes, yes, yes. So that one is continuous. Okay? Okay, let's look at a composition of functions. This looks terrible, but when we're done with this, we'll look back at it. I'm just going to give you, so you don't panic. We'll look back at this and say, couldn't we have done that more easily? Couldn't we have just thought about this more intuitively and maybe avoided a lot of this abstraction? But we want to see it both ways. So you guys know what that operator means? Open circle like that? What is it? G of, okay, good. So G of f of x, right. A better way to write it is this way. Okay, G of f of x, that's more intuitive. Okay, so let's ask ourselves this. Is f of x continuous at 0? You guys are really paranoid about making a mistake. Don't be. What do you think? Everybody vote with your thumbs. Is f of x continuous at 0? What's your intuition telling you? Yeah, it is, right? Why wouldn't it be, right? I mean, look what f of x is. What kind of graph is that? Yeah, and we can think of it as a quadratic, right? It's just a parabola. Is there any place where I'd pick my pen off the board to graph a parabola? No, nowhere, right? It's fine. The answer is yes. Okay, here's g of x. Is g of x continuous at 0? Yeah, absolutely, right? I can plug that value into the function. It works fine. There's no problems here. Where would there potentially be problems? Where I divide by 0, or I take a root, an even root of a negative number. Or if I had some piecewise function, we'd have to worry about whether the pieces met up, right? But this is fine. Okay, so then is g of f of x continuous at 0? Seems like it should be, right? Okay, but it's not. But it's not, because g of f of 0 is literally that. There's two parts to it. It's g of f of 0. The value that we're feeding the inside function is 0, right? F is going to spit out a value. The output of f becomes the input of g, doesn't it? Everybody see that? Okay. So the output of f becomes the input of g. What is f of 0? Let's calculate that. Okay. F of 0 equals -4. So g of f of 0 becomes g of -4, right? Okay, well, is g continuous at -4? No, clearly not, because the function is not defined there. So it can't be, right? I'm going to have to pick my pen off the board. Okay, so what's the moral of the story there? Well, if you have a composition of functions, you got to remember it's a train. The inside functions, you're going to feed the inside function a number. It's going to spit out a number that becomes the input of the next level of function. If you have you have a composition of many functions, you got to do that several times. Okay, but look what happens here. Seldom would you look at these two things separately like this. Sometimes, we just did, but if we wanted to calculate g of f of x, we would probably go back here and say, okay, well, what would that be? G of f of x means I'm going to plug in f of x into this pattern, right? So g of f of x then is just going to equal, what did we say a couple of years ago? When we're plugging things into functions, we always open up a set of parentheses for dumping in the value, right? So every place I had an x in the function g of x, I'm now going to dump in an f of x, right? So really what that means is the cube root of, instead of an x, that's going to become an f of x, right? Plus 11 divided by, instead of an x, it becomes an f of x plus 4. Well, what is f of x? It's x squared minus 4, right? So this is just equal to x squared minus 4 plus 11 over x squared minus 4 plus 4. If we simplify that function, there's not a whole heck of a lot to simplify there, but if we do, what do we get on the top? We get x squared plus 7 inside the radical. What do we get on the bottom? X squared, right? So g of f of x, we might call that the single function h of x, which is that new function. Now we could have answered the question, is g of f of 0 defined? Well, that's the same thing as saying h of 0, my new function. Well, no. Now we can see it pretty clearly because I've got an squared on the bottom, right? So is there any reason to panic about this? Not really. I want you to see what we did, but in reality, if we build this composition of functions, it's going to be obvious just by inspecting the function where it's defined and undefined, or continuous and discontinuous, right? Okay. Okay, so Well, I mean, today's just kind of introductory stuff. So now at last we get to the point where we could say a function is continuous on an open interval. So we're going to extend this. It's continuous on the open interval where x is greater than a and less than b if it's continuous at every point in the interval. No big deal, okay? So we could already say something important about types of functions. Polynomials are what we call well-behaved functions in math, and that's literally how we describe them. Polynomials will never have a place where I'd ever have to pick my pen off the board. Okay, there's no chance of ever having to divide by 0 or take an even root of a negative number in a polynomial. So polynomials are defined everywhere in their domain, which is all real numbers. Polynomials are always continuous on their entire domain. What about rational functions? Same thing. Rational functions are ratios of polynomials, right? So every place where the top polynomial and the bottom polynomial are, let's say this differently. Here's a rational function. R of x is a rational function. It's the ratio of the polynomials p of x and q of x. Those are polynomials. Is p of x ever going to cause any problems? No, because it's on the top of the function, right? Is q of x ever going to cause any problems? The only places where q of x would cause a problem for my rational function is where q of x has a value of what? 0. And I would have to exclude those from the domain, agreed? Because I can't divide by 0. So then every place in the domain, we should be fine, right? Because every place in the domain, if we exclude all the zeros of q, all the other outputs of q are going to be real numbers. The outputs of p are going to be real numbers on the top, and that's fine. As long as the bottom is not 0, I don't have any issues there, do I? So long story short, rational functions are continuous at every point in their domain, okay? That helps us a lot. We don't even have to think about those kinds of functions. We automatically know they're continuous every place they're defined. Okay, so how about this function then? We've got a rational function. Tell me the intervals over which the function is continuous, and I'll give you a hint. The easiest way to find the intervals where it's continuous is to find the points where it's discontinuous, and those will divide the intervals. So what are the points where this function would be discontinuous? -2 and 0, right? The zeros of the denominator, done. Every place else, it's continuous. Okay, we'll get back to this. Why don't you guys take a couple days off? We'll come back on Monday and get back to this stuff, all right? Yeah, I try to be real kind.